Now let's discuss one more important interpretation of the complex number. It's called a trigonometric representation. And its nature related to a geometric representation. For example, here is our complex number z, represented by the arrow in the complex plane, with coordinates x and y. Z equals x plus iy. And the trigonometric representation of this number is obtained while switching from Cartesian coordinates to polar ones. So let's introduce the modulus of z vector and the polar angle phi, which is the angle between the vector representing the complex number and the positive direction of their x-axis. This way, x now equals r cosine phi, while y equals r sine phi. And now our complex number is represented as r times cosine phi plus I sine phi, where r is obviously a modulus of the complex number, while angle phi is called an argument of the complex number. The argument is a very important characteristic of a complex number. You probably noticed that there is a kind of ambiguity here, because the argument is defined modulo 2 pi n, where n is an arbitrary integer. This ambiguity doesn't cause any problems when we deal with complex algebra, but it will become a very essential property once we switch from complex algebra to the theory of complex functions, and especially the theory of multivalued complex functions. And therefore we'll always keep it in mind. But now let's study how different operations with complex numbers affect its trigonometric representation. For example, complex conjugations. Z star is defined as x minus iy, and turning to polar coordinates, we obtain r cosine phi minus I sine phi. Now pay attention, this is not a legitimate trigonometric representation of the complex number, because of this minus sign in front of sine function here. In order to turn it into a true trigonometric representation, we need somehow to absorb this minus sign. And to do so, we need to use symmetry properties of our trigonometric functions. We can rewrite the sum as cosine of minus phi plus I sine of minus phi. And this is a standard trigonometric representation, which tells us that complex conjugation retains the modulus of the complex number intact while changing the sign of its argument. And indeed, you can clearly see it from a geometric representation. Angle phi is switched to angle negative phi. Now let's see how multiplication and division of complex numbers is expressed via their trigonometric representation. Suppose we have two complex numbers, z1 and z2, expressed in their trigonometric form. Now let's multiply them. And we see that in the braces we obtain the following combinations of cosines and sine. And we see that the real part of the obtained number can be combined into a familiar from trigonometry formula. It's simply a cosine of phi 1 plus phi 2. While the imaginary part can be organized into sine of phi 1 plus phi 2. And we see now that our newly obtained complex number is again expressed in a trigonometric form. Its modulus now is equal to the product of moduli of the constituents of this complex number, r1 and r2, while its argument is obtained via a simple summation of the arguments of its constituents. So when we multiply two complex numbers, their moduli are multiplied while their arguments are summed. Now let's establish a similar rule for the division of two complex numbers, z1 over z2. Now let's multiply both parts of this fraction by z2 complex conjugate to obtain modulus of z2 squared in the denominator, which is very suitable because now we have a real number in denominator. But now we have a simple multiplication in the numerator, and we already know how to do this. The only difference from the previous case is that now the argument of the second complex number flipped its sign. So we obtain in the numerator the product of moduli r1 and r2 times cosine of phi1 minus phi2 plus I sine of phi1 minus phi2 over r2 squared. And cancelling r2 in numerator and denominator, we obtain our new complex number, which is again represented in its trigonometric form. We see that its modulus is obtained via the division of the moduli of its constituents, while its argument is obtained as a subtraction of respective arguments. And now we conclude that when we divide two complex numbers, the modulus are divided while the arguments are subtracted. And now let's practice a little bit. For example, we have a complex number with unit modulus. Z0 equals cosine theta plus I sine theta. Let's raise it to the second power. Z0 squared will be equal to cosine of 2 theta plus I sine of 2 theta. Obviously, the modulus of the new complex number will again be equal to 1. And from this, we can easily conclude that once we raise Z0 into nth power, we'll obtain cosine n theta plus I sine n theta. And this is the celebrated Moivre identity. Now let's consider one more example. Let's find the trigonometric representation of the following complex number, minus 1 minus I. Well, first of all, its modulus is equal to square root of 2. Now we factor out this modulus to obtain in the braces minus 1 over square root of 2 minus I over square root of 2. And this expression in the brackets is, according to our trigonometric representation, equal to cosine phi plus I sine phi. So now we have two equations. Cosine phi equals minus 1 over square root of 2, while sine phi equals to, again, minus 1 over square root of 2. And now we need to solve this trigonometric system. But of course, as we mentioned earlier, phi angle is defined modular 2 pi. So whenever we deal with arguments, we will always try to specify a particular domain in which this argument is defined. It may be from 0 to 2 pi, or from negative pi to pi. It all depends on a particular problem. So don't get confused by it. In this situation, let's choose the argument belonging to the strip from negative pi to pi. Now our cosine equation has two roots, plus minus 3 pi by 4. Our second equation tells us that the sign of the argument should be negative, so we opt for minus 3 pi by 4. And here is our final trigonometric representation of this complex number. It's square root of 2 times cosine of negative 3 pi by 4 plus I sine of negative 3 pi by 4. Also, never hesitate to use geometric representation just to help you. For example, if we plot this complex number in a complex plane, we'll immediately see that it's positioned in the third quadrant. But now, of course, it's quite trivial to read out the argument of the corresponding complex number, namely minus 3 pi by 4. So let's practice a little bit more. And let's address some truly simple cases. For example, complex number 1. Its modulus is equal to 1, while its argument is equal to 0. Well, what about complex number negative 1? Again, its modulus is equal to 1, but its argument is equal to pi or negative pi, depending on your definition. Complex number I. Again, its modulus is equal to 1, while its argument is pi by 2. What about complex number negative I? Well, again, its modulus is 1, but its argument is either negative pi by 2 or 3 pi by 2, depending on your choice. So this is how trigonometric representation works for simplest complex numbers, so you need to get used to it. And our final example of trigonometric representation is the complex number 1 plus cosine theta plus I sine theta. As before, we need to find its modulus and its argument. And here I'd like to show you how geometric representation can still be useful even in this task. So let's plot complex numbers 1 and cosine theta plus I sine theta. We remember that this complex number has the modulus 1 and its inclination is theta with respect to real axis. And now it's very easy to sum up these two vectors using triangular rule to obtain our complex number. And we see that what we deal with here is an isosceles triangle with side angles equal theta by 2, and its base trivially found from trigonometric consideration. It's 2 times cosine of theta by 2. And here it is, we obtain the modulus of this complex number, 2 cosine of theta by 2, and its argument, theta by 2. And of course, you may obtain the same representation using purely algebraic means. For example, 1 plus cosine of theta can be represented using doubling formula as 2 cosine squared of theta by 2, while sine theta is split into 2 sine theta by 2 times cosine of theta by 2. And once we factor out 2 cosine of theta by 2, we obtain the same trigonometric representation. And that's it for trigonometric representation. In our next video, we'll see how it opens up for more important and widely used in complex analysis exponential representation. So stay tuned.